Hi there, my name's Andrew Brown. Welcome to the second video in our series Real-Time Music and Sound with Pure Data. In this series we're looking at audio synthesis and sequencing in the Pure Data environment. We're using Pure Data Vanilla, so if you don't yet have the software you can download it and get going along with us. In today's video we're going to be looking at the basics of hearing and seeing audio signals in Pure Data. However, before we get to audio, I wanted to start with some other basics about how Pure Data works as a visual programming language. If I create a new object, I can go to the Put menu, select Object, put it on the screen. You'll see that it follows my mouse around. You'll also notice that it's an empty object and we need to give it a function. So I'm going to start with some basic mathematical functions. So I'll put multiply in there and click outside the box and it resolves itself. So we now have a multiply object. The multiply object has two inlets indicated by these black markers at the bottom. So it's going to multiply together two numbers. And it has an outlet where the result of that multiplication will be sent. So we can send some values into the multiply object. I'm going to use for those values a message box. So I create a message box and I connect one to the right inlet. It's waiting for me to put some message in there. In this case, a multiply function takes, of course, numbers as input. So I can put a number in there, 23. I'll create a second message box, connect that to the right inlet and put another number in there. So we now have two messages, two numbers in this case, which are going to be sent to multiply. The outlet, we can put a number box and connect that up, and that will show us the value of the multiplication. So just to reiterate, we've got three different box types here. There's the object box, which is used for functions. There's the message boxes, which are used to pass values into functions. And there's a number box, which is used to display or to send numbers. So in order to evaluate this, I'm going to hold down the command key on my Mac, click 567, then click the 23 message box, and you'll see the value appears down there. One thing to notice was that the value only appeared once the number 23, the one that's going into the left inlet, was executed. If we change this number box just to some other value so we can see that it resets, if I click again on 567, you'll notice that nothing actually happens in terms of the multiply doesn't evaluate. This is an important feature of PD, that the leftmost inlet, when we click it, you'll notice that then the number did evaluate. The left inlet on almost all objects is called the hot inlet, or the kind of active inlet. When a message is received in that left inlet, then the function will execute. In any other inlet, and you can have multiple inlets, when the values go in to the function, they're just stored as arguments to the function, and then when the function receives an argument in its leftmost inlet, then the argument is then the function is executed and the result comes out. One other thing that I did there was to click and scroll in this number box. That's a particular feature of number boxes. Their values can be changed in this way, and that can be useful for adjusting things. Notice if I do the same to the message boxes, it does not happen. The messages are fixed unless I go in there and I type a different message, then I can reevaluate the multiply with the new message. What you will notice with the message boxes, when I click on them, they flash just to indicate that they're actually sending their message down the chain. So those are some of the basic elements, the most important of which is that the left inlet on these functions is the hot inlet, which executes the function. All right, let's move on to some audio. I'm going to delete these boxes. I draw a rectangular box around the outside and select all of those things. You'll notice that they become a sort of a blue shade of blue to indicate that they're selected. If I press the delete button, then all of those objects are gone away. We're back to a blank patch. So let's do some audio. Create a new object box. I'm going to create an oscillator. It's OSC tilde. Click outside of it and the box resolves. The oscillator has two inlets and an outlet. In this case, the oscillator inlets are the frequency and its phase, and the outlet is the audio signal. One thing to notice about the oscillator object is it's OSC tilde. This tilde symbol is used throughout Pure Data to indicate audio objects. So objects which don't have the tilde are generally not audio, they just process data, but audio objects are shown with the tilde. We can see this reasonably clearly, for example, with the multiply object. When I was doing the math functions before, we just used a multiply object like this without a tilde. And that allowed us to process data like the numerical data that was passed to it. If we're going to use a multiply object for an audio signal, which we want to do as a volume control, then we'll use a multiply tilde object. If, for example, we try to connect this oscillator's output to this particular box, just the multiply, you'll see that it doesn't connect, and in fact over here on the PD window we get a message, can't connect signal outlet to control inlet. So that just is reminding us that that's an invalid thing because there's an audio signal coming out here, and this box without the tilde doesn't accept that audio signal. However, the multiply tilde object is designed to process audio signals and it will connect. Let's just put a message box here passing a number into this object to show one other thing which is there. The other difference is the type of connection. So we can see that there's a subtle difference between these two connections. The audio connection line is slightly darker, slightly thicker than the data connection line. That is another visual indicator that we're working with audio signals with the thicker line and non-audio signals, just data signals over here. Okay, so we have our oscillator, we have an amplifier, the multiply thing, and we will send the output of that to the digital to analog converter, the DAC, which is our audio output, left and right, because we operate in stereo by default. Okay, so far, but we still can't hear anything and we can't see anything on our oscilloscope. There's two reasons for that. One is we have no frequency for our oscillator. Well, in fact, we have a frequency of 0, which is very low. And we have a volume of 0 as well by default. And so we've got no volume and effectively no frequency. So let's put numbers into those to work all of that out. First of all, we put a number box above our oscillator and connect it to the leftmost inlet and click and scroll up. Then we get a number, this is now 512 Hertz going into our oscillator. We still hear nothing because our volume is at 0. So we create another number box, connect it to the left inlet of the multiply, hold the shift key down and scroll up, and here we go. We start to hear an audio signal at 512 Hertz. If I drag on that, change the value, and so we can change the frequency and the amplitude by varying these number boxes as they go in. So that's how to create some simple audio. We can see on the oscilloscope over here what that signal is. But this oscilloscope is not actually part of Pure Data. It's a separate program called Signal Spy, which I'm using for these videos just so we can see what's going on. But it turns out that in PD we can also create a visualizer to show that signal. So let's do that now, because it's a very handy feature if you don't happen to have an oscilloscope handy. We're going to use for that an object we haven't yet seen in this video, and that object is the one right at the bottom of the put list, the array. An array is like a big list of values. In this case, the array starts with asking us to specify some properties. That's its name. We'll leave the array1 default name for now. And as I said, an array is like a big list. In this case, the size is 100. We might make it a little bit bigger. Let's go 500, because we're going to be showing individual samples. And then there are different drawing modes. We're going to choose the polygon drawing mode. So we say OK, and our array appears. So this will visually show what's going on. The array is like a two-dimensional object with values, amounts up on the x-axis and our positions from, in our case, 0 to 500, because we specified it to be 500 long, along the y-axis. By default, the array's value scale goes from +1 down to -1, with 0 being in the middle, which is perfect for us for audio. So we want to be able to send information from our oscillator into the array. You'll notice the array does not have an inlet, so it's not the sort of thing that we can just connect straight up. So we need to use another object to do that. So we create an empty object, and the object that we want in this case is called tab_right. So an array is sometimes also called a table, and so this is table_right, tab_right. Tilde indicates that it's going to be an audio signal that we're dealing with. And tab_right needs to take an argument, which is the name of the array to which we want to send the data. In this case, our array is called array1. I'm going to move that across here. So far so good, and we can connect our audio output to tab_right, and it's almost there, but we still notice that we can't see anything yet. That's because we need to actually tell tab_right to send the data. We tell it to do that using another object, which we've not yet seen in this video. This other new object is called a bang. A bang is just like a trigger, and the trigger in this case will ask tab_right function to execute. So when I connect it and then click on that bang, you'll see that the waveform starts. I can turn the amplitude up, click, and that amplitude will be there. Every time we bang the tab_right object, it redraws, and because the phase is constantly changing, we can see some movement there. So okay, so this is pretty good, but it's a little tedious to have to keep triggering this tab_right. So we want to automate that triggering process. I'm going to use another object, which is called metro. Metro is short for metronome, so it will give a regular metronomic pulse. And it wants a kind of speed, if you like. In this case, it's like an interval duration between the metronome outlets, and it's in milliseconds. So we now have a metronome which is going to send out a pulse every 100 milliseconds. I connect that to our bang. We can see that that's not yet working because we need to turn our metronome on. To turn the metronome on, we use yet another new object in this tutorial. It's called a toggle. The toggle simply turns on and then off. If I position it here and connect it to the metronome, when we click on the toggle, it sends a value 1 or an on value to the metronome, and you can see now that it's operating as we expect. So it's regularly being updated and changing the visual appearance. If we change things like the frequency, we can see that that is mirrored in our array-based oscilloscope. We can also vary the amplitude and we get a similar updating. If we want to stop the metronome, we just click the toggle a second time and that stops the metronome from operating, and you'll see that we now have a static waveform because it's not being updated. We can restart it anytime we like. And so we now have a way of visualizing within PD our audio signals, and being able to see them is a really handy feature. It's why I've included this oscilloscope here in these video series, because being able to see the audio that you're working with is, as you can imagine, a very, very handy feature indeed. A couple of other things to say about the way in which I've been adjusting these values in the number boxes. You'll notice that the frequency value I've been increasing as an integer, so we just get whole numbers, whereas the amplitude is being increased as a fractional number, as a floating point number. In order to do that, I need to hold down some different keys as I'm doing that. Importantly, to get the fractional numbers, I'm holding the shift key down. But those of you who are watching carefully may have noticed that I'm always holding down on the Mac the command key. And then here for fractional, I'm holding command and shift. So there's two things going on here. The shift key is necessary for fractions, but the reason that I'm holding down the command key is because our patch is currently in edit mode. When it's in edit mode, I can do things like move objects around, I can create new objects, I can update what they might be. For example, I might change the oscilloscope into something else. Maybe I'll just use a plus tilde object, which makes no sense whatsoever, but you can see that we can edit away as we like. If I hold the shift key down in the number box, we get fractional numbers. If I don't, then we just get integer number changes. Okay, so the question is, why do I need to hold down the command key when I'm in edit mode? It's because you can see in the top of the patch, it says that we're in edit mode. If we go out of edit mode, command E will do that for us as a shortcut, then I can change those values without holding down the command key. I still need to hold down the shift key to get my fractional numbers, but I can't grab any of these other objects and move them around because in edit mode those things are sort of frozen. So when you're out of edit mode, you're basically kind of in, play mode, performance mode. I like to think of it as this is the mode that you want your patches to be in, when you're performing on stage or you're doing some production work with PD, so that you don't sort of just change everything, you're just simply adjusting variables, turning things on and off as we go. To get back into edit mode, we can use the shortcut command E, and now everything is re-editable again as we go. Just to remind you, we can save patches and we can reopen patches just as you would expect in any software. So this means that all of this effort to create this oscillator patch, we can save it, reload it later on, and we're good to go. Okay, just to finish up in this video, let's just have a look at a couple of other audio sources that are in PD as well as that oscilloscope. One of them is just a noise generator, and those of you who've worked with any synthesis will know we need oscillators, and also noise generators are very popular for synthesis sounds. So if we turn that up a bit, and here we just get white noise. And so on, you can see the white noise in our array based oscilloscope. And so there we have it. We've got oscillators, we've got noise generators. A third type of audio we can use audio from an external source using the analog to digital converter. So the analog to digital converter is in a sense the inverse of the digital to analog converter. So it's taking in an external input from our microphone, converting it to a digital signal and passing it in. In this case, for my computer, that ADC defaults to the microphone. So as I talk, you can see that it's capturing my audio signal and displaying it on the array. Hello, testing 1, 2, 1. So that's going to be really handy when we want to do other things with external audio coming in. So we've seen in this video that we can get input from an oscillator, which will give us a sine wave. We can get input signals generated by noise, and we can get audio in. In a later video we'll have a look at other kinds of waveforms and how we can construct those, but these are the basic building blocks that are available to us in PD. So give all that a go, and I will see you in the next video. Thank you.